So this video is talking about the uniqueness or the existence theorem. It's actually a two-part theorem. First part talks about existence. Second part talks about uniqueness, and that's in terms of solutions to differential equation. So when you think about a differential equation of the form dy dx is equal to x, where y is the dependent variable and x is the independent variable. We could talk about the existence of a solution at a certain point. So that's what the existence theorem is about. It's a quick little test where we can establish whether there is we know whether there's a solution to this differential equation at that point. Okay, so now there's three cases, the three possibilities, I guess you should say, when you're dealing with a differential equation. First case is there's no solution at a particular point. So that's a possibility. Now we of course could still have lots of solutions to the differential equation, just none of them go through that point. So we're talking about specifically about a differential equation and a certain point on the coordinate plane. Okay, so I don't know why that's there. Oops. Okay, so the second possible case would be that there is infinitely many solutions through a point. So it's possible that I have a differential equation that, and we're checking at a certain point, it's possible that there's an infinite number of solutions that go through that point. Then, of course, the third case is one unique solution in a neighborhood of the point. Now this neighborhood, of course, we're talking about like an open neighborhood, not a closed neighborhood. Those are my three possibilities. I could have no solution at a particular point. I could have infinitely many solutions through a point, or I could have one unique solution in a neighborhood. And the reason why we say in a neighborhood, meaning that this is some old stuff from an earlier video. Sorry about that. The reason why we say neighborhood is because if we're talking about a point, we're saying that, of course, as we've talked about with slope fields, when we're drawing slope fields, we start somewhere and just kind of see where they go, right? So what we're saying is that there is this point, A, comma, B, and we have this little open neighborhood around it, where we're saying there's only one solution that goes through that neighborhood. Okay? All right. So here we go, the existence theorem, part one. So part one is we're testing for existence. Okay? Oh my goodness. Okay, I'm going to switch to another page so I don't have to keep erasing this stuff. Okay, so existence. Part one. So if f of x comma y, this is a differential equation. So we're talking about dy dx equals f of x comma y. Okay? Yeah. If f of x comma y is continuous on an open interval around AB, then okay. Sorry, my son was singing in the room next door, so I had to get him to stop. So let's see where were we? On open interval AB. So if this is true, if f of x is continuous on an open interval around AB, so we're testing for existence of a solution that goes to this point, and it's the solution to that differential equation. Okay. If this is true, if this function right here is continuous on an open interval around AB, then at least one solution exists. Around x equals a. Okay? So, if f(x) is continuous on an open interval, now the open interval is important because if we have a function that, for example, comes up and ends at my point, then there's no way to get an open interval around that of a continuous open interval around that, because there's nothing on the other side. So that's why we say open interval, because if we said closed interval, you could possibly set up something like this, and it would be continuous the whole way because we're not looking on the other side of it. So essentially what the open interval does is eliminates the possibility of a cusp or an endpoint, right? So what we're trying to say is that if this function just comes up and ends at a over b, or a comma b, then that it does not fit the requirements of this equation. So that's why we have to have an open interval. So however, if it is continuous on that open interval, then at least one solution exists around x equals a. If not continuous, on the open interval, on a open interval, I mean, you can create the open interval, on a open interval, then no guarantee. Notice it doesn't, I forget how you spell guarantee. Guarantee. Notice it doesn't say that one doesn't exist, it doesn't guarantee us existence. So if it passes the test, that means there's at least one. If it doesn't pass the test, then we essentially don't know. There's no guarantees. Okay? So that's the first part of the existence of this test. The second part is testing for uniqueness. Sorry. Uniqueness. So we're going to do the same test, roughly. It's the same test, but instead of on the function, we're going to take the derivative of the function, the partial derivative of the function, so I should have went like this, with respect to y. Now, if you haven't had Calc 4 yet, you don't know what a partial derivative is, so I'm going to take a little bit of time to explain that. So a partial derivative, all that says is that we take the derivative with respect to y. So we're only considering y to be a variable. So any other variable that's in the expression is considered to be a constant. So for example, if my f of x comma y was 3xy. Now normally when I take the derivative of that, I'd have to use, if I took a normal derivative of that, I'd have to use the product rule, right? And the derivative of this thing would be the derivative of 3x times the derivative of y. I'm sorry, the derivative of 3x times y plus the derivative of y times 3x, because both of these are variables. But in partial derivatives, we're taking the derivative with respect to y, and we're holding everything else a constant. So in this case, if I was to take the partial derivative of this thing with respect to y, that means x would be considered a constant. So we just have a constant times y. So the derivative of this thing with respect to y would just be 3x. Okay? Well, let's look at another example. Let's say f of x comma y is equal to, let's say 3x y squared plus 4x squared. Okay? Now, if we're taking the partial derivative of this thing with respect to y, then this first one is just a polynomial, or a power rule, right? That'd be 2 times 3x, which would be 6x, times y to the first power. But the derivative of the second part, the derivative of 4x squared, is just 0, because we're holding x as a constant. So the derivative of this expression would be just 6xy. Okay, so that's a quick little crash course on partial derivatives. The uniqueness test says we take the partial derivative of the f of the function that's set equal to dy dx, and then we apply the same criteria. So this thing, if this is continuous on an open interval around, whoops, I left off the end, around that same point, a comma b, then there is a unique solution. Which means there's only one solution. So if this expression, after we've taken the partial derivative, if it is continuous on an open interval around the point that we're checking, then there is a unique solution. So that's the test. And there's a lot of words to this, and you might need to re-look at think about again what continuous and open intervals and stuff like that means. So you might want to go through and watch the video a couple times. But let me do a quick example. So let's say we have dy dx is equal to 3y 2/3. I'll just do that for now. Okay. So let's say we're checking at the point 0, 0. Okay. So what we want to know is we want to find out some information about the existence of a solution to this differential equation that goes through that point. So the first thing is I'm going to check for continuity. So so remember my function that I'm looking at is f of x comma y is 3y to the 2/3 power. Whoops, I said 2/3. Now the question is that continuous? Can I find an open interval around 0, 0 where this function is continuous? Well, this is continuous for all values of y. And notice there are no x values in this thing, so we don't have to worry about the x's. So since this is continuous for all values of y, then it is certainly continuous for y equals 0. And we can easily find a neighborhood around y equals 0 where it would be continuous, because it's continuous everywhere. So that means at least one solution exists. And again, that's one solution to this differential equation that goes to that point. Okay? So that was part one, test for existence. Now we're going to test for uniqueness. So we know at least one solution exists. Now we're going to test, is there a whole bunch of them, or is there only one? And that's what the uniqueness part does. So now we're going to take the derivative, partial derivative of this. So the partial derivative of 3y to the 2/3 power with respect to y. Well, 2/3 times 3 would just be 2. Drop the power 1, and that would be negative 1/3. So really what we have here is 2 over the cube root of y. Now, again, we're going to test for continuity. Well, this function is continuous everywhere except at y equals 0. So this thing is not continuous at y equals 0. So which means I certainly can't put a neighborhood around this point that would have a where this would be continuous. So this fails the uniqueness test. So we're left with that there is at least one solution to this, but there may be more. We don't know because it failed the second part of the test. All right. So hopefully that makes sense. If you have some questions, go ahead and email me, and you can start working on the worksheet that there's about, I think, about 4 or 5 or 6 problems that are just like this, where I give you the differential equation and a point and ask you to test for existence of a solution and then test for the uniqueness of that solution.